in this problem, we have a kid on a swing. So say you pull back the kid to an angle theta and then release him to swing through the bottom. We want to know, we're given length of the swing, mass of the kid, and angle of the initial pull. What is the speed at the bottom and the tension from the swing rope at the bottom? Well, for this, we can use conservation of energy for part A and Newton's method for part B. So we know that there's no external work or friction done here. So energy's got to be conserved from states 1 to state 2. So for the procedure, state 1 is free body diagram. So let's say here is the kid on the swing. We know that we've got his weight pulling down. We know that since he's swinging in a circle, we'll also have that centripetal force. Except in this case, the R is actually L. And we've got tension from the rope pulling up. Step 2 is assign the coordinate frame. So we'll say that here is the 0 point. Y goes in this direction. And 3, write equations. So from 1 to 2, energy is conserved. So we know that energy at 1, say potential energy at 1 plus kinetic energy at 1 equals potential energy at 2 plus kinetic energy at 2. We're doing part A right here. Well, all right, so it's state 1. Does the kid on the swing have kinetic, potential, or both types of energy? Well, he's not at 0, so he definitely has potential, but he's not moving, so there's no kinetic. Now, at state 2, let's see, he's not at 0, so he does have potential. Now, because he's below the 0, so energy, potential energy 1 and 2 are both going to be negative. That's okay because they're below the ground, or not the ground, they're below the swing set where we put the origin. Now, kinetic energy, it will also have, because he's going to be moving. So, potential energy at 1 is going to be, that mgh is the formula, so we'll have mass, gravity, and what is his height? Well, here, it's going to be related to the length of the string. So that component of that length in the y direction is going to be the cosine. Cosine theta times L, but this is negative because it's below the origin. This equals potential energy at 2, which in this case will just be minus mgl plus 1/2 m v squared. Well, very conveniently, masses cancel. If we rearrange, then we get g L times 1 minus cos theta times 2 equals v squared. So then we put numbers into here. 2 times 9.81 times 4 times 1 minus 1 over square root of 2, all square rooted, equals v, 4.79 meters per second equals v. So he's going 4.79 meters per second at the bottom. And this will be where his fastest velocity is because that is where his lowest potential energy is. So at state 1, he has all potential. State 2, he's got some potential and some kinetic. Anywhere else, he will also have potential and kinetic, but his lowest potential is at state 2, and so that's his highest kinetic because energy is conserved. There's just this trade-off. Energy can't be created or destroyed, it can only change form. So it's changing form between potential and kinetic. Max kinetic is at 2, max potential is at 1. Now for part B, we need to find tension at the bottom. Well, we know that here at the bottom, because the rope is not wrinkling, the acceleration in that y direction is going to be 0. He's not moving up or down. At this point, his velocity is to the side. So we'll have sum for the forces in the y equals 0. So we have tension going up, centripetal force going down, weight going down. Then T equals m times v squared over L plus G. So then we put numbers in. T equals, let's see, 40 times 4.79 squared over 4 plus 9.81. This equals 622 newtons.